to all viewers. My name is Alexandre Giron, and I will present the work entitled An Entropy Source Based on the Bluetooth Received Signal Strength Indicator. This presentation is organized as follows. First, the motivation is presented, followed by related works, objective, methodology, result and discussion, and finally the final remarks. This work is related to the random number generation for IoT devices. The random number generation is considered as the Achilles heel in cryptography. The security of a crypto system depends on the quality of the random number generation. Typically, computers collect randomness from a pseudo-random number generator, which needs a seed, and therefore physical sources are used to feed the pseudo-random number generator, such as sound and network cards, disk access times, among others. These are called the entropy source. Internet of Things devices may not have these sources available due to constraints such as performance and energy consumption, and also security. One example of Internet of Things technology is the Bluetooth Low Energy, which brings connectivity to a broad set of products. The main problem is that there are few entropy sources available for IoT devices due to hardware constraints. In addition, relying in a single entropy source could be risky. Users must trust in closed hardware designs that they could not have a backdoor violating their privacy. Another risk that must be considered is that hardware failures can happen, and security flaws can happen also. Another issue is when the environment is used for extracting randomness, they must be evaluated in order as the quality of the random number generation from the environment. Attempts to solve such problem are presented in the related works, but the focus here is on wireless communications, where a measure called the Received Signal Strength Indicator can be used. Some works used this measurement to extract shared keys in the context of key generation, and they did not evaluate it in practical experiments. So, the objective of this work is to find an alternative entropy source for the IoT context. The constraints of IoT devices should be considered, in addition to the secondary goals, such as evaluation techniques for extracting randomness from the environment, without adding new hardware components or new peripherals to that. In addition, provide implementation and practical experiments to this evaluation, and also compare it with other sources from the literature. IoT devices often depend on wireless communication. Bluetooth Low Energy is a popular technology used in IoT, so it is the main technology used in our methodology. In the center of the figure, Raspberry Pi 3 device, in this case, uses our proposal called Bluerandom. It scans for nearby devices in order to collect the randomness from the environment. Our proposal is called Bluerandom since it uses the Bluetooth technology and uses the Received Signal Strength Indicator measurements for the random extraction. These measurements look unpredictable due to several factors, such as the variation of the measurements caused probably by interference, movement of devices, and fading present in wireless communications, and also due to low-level communication between the hardware modules. In the experiments, a Raspberry Pi device measured 1 to 8 nearby Bluetooth devices. In the evaluation, we developed 4 experiments with 3 random extractors. These random extractors, we could use a hash function or chaotic functions, but here we selected 3 extractors. One is the well-known von Neumann extractor, where the second is odd or even difference from the measurements, and the third is just odd or even when the measurement the Bluerandom outputs are 1 if the measurement is odd and 0 otherwise. In the case of von Neumann, we adapted to use the last digit fluctuation between 2 consecutive measurements, where for each bit pair we apply the von Neumann extractor. The results are presented in the table from the experiment 1. In the experiment 1, we evaluate Bluerandom outputs alone using FIPS tests. In the first scenario, we use a 5-layer Faraday box where each one device was used. And in the other scenario, we variate the number of devices present in the scenario. We can see in the third column that using the just order even random extractor, that scalability is presented, where increasing the number of devices, the pass rate of the results from the Bluerandom increases, which is a suspect of scalability from our proposal, where increasing the number of devices, the quality improves. The same happens when we measure the channel entropy using bits per byte metric. The more close to 8, the better, and using the third extractor, we can see that the entropy increases by increasing the number of devices. In experiment 2, we compared the Bluetooth internal pseudo-random number generator with Bluerandom feeding seeds to a pseudo-random number generator. It was evaluated using this software, and we can see in the table, in the last column of the table, that the results are similar between the internal Bluetooth generator from the device compared to AES and SHA-256 using seeds from Bluerandom. These are satisfactory results for Bluerandom. In experiment 3, we compare different entropy sources for a pseudo-random number generator, in this case SHA-20. We used the die-harder test suite for the evaluation, and we can see in the table that the results are very similar between the entropy sources, which is another indicator that Bluerandom could be used as an additional source of entropy for the system. The last experiment performed in this work is using the Bluerandom as a source for entropy in the Linux entropy pool. We can see in the figure that there is a growth in the entropy count when using Bluerandom. However, we can state that in this case the Raspberry Pi 3 was configured to have limited network activity and no peripheral attached, so we can compare the entropy pool with Bluerandom and without Bluerandom. In this such scenario, which simulates a very limited IoT device, using Bluerandom can improve the entropy count in the system. Lastly, Bluerandom is compared to the literature regarding the throughput. The Bluerandom configuration selected was with 4 devices, and we can see that in average 1 byte per second is the throughput that Bluerandom can achieve. Other generators can achieve more throughput, but we can see that the byte entropy is very close to the other generators. Final remarks, we can state that Bluerandom has a scalable entropy source, where the quality of the output can be improved when more devices are nearby to the device that is using Bluerandom. It is important to note that it can be used as an additional source, not the only one in the system, because it does not pass in the FIPS test in 100%, and so we recommend to use as an additional source. The main advantage of Bluerandom is that the environment is explored for randomness instead of adding more hardware components, which could impact cost and energy consumption in the device. For future works, we considered using other metrics of wireless networks, such as link quality indicator, and also other wireless technologies for evaluation. That being said, I thank you for your attention, and I am now open to questions. Thank you.